Let's look at the error detection and error correction at the data link layer. Maybe you may refer the book on page 257. From 257, you can see that error detection and the correction method in the data link layer. Um, the location of the data link layer in between the network layer and the physical layer. So it provides the services to the network layer when it receives the bit from the physical layer, and then forming the frame, and then take the data to the upper node or upper net layer, such as third layer or the network layer. So actually the data link layer receives services from the physical layer, and then encapsulate and decapsulate should be provided. And one of the important things is that in framing, from when delivering data from the network layer, it should form the frame, and then between the node, this frame will be delivered. Okay, while sending and receiving the frames, it needs some kind of flow control and error control, and even some congestion control. So in this lecture, let's look at what is the concept and method of the flow control and error control in data link layer. The flow control actually frame transmission rate usually larger than the destination processing speed. What does it mean? For example, here this is the sending node, and the frames are pushed to the receiving node. Unfortunately, if the processing speed of the destination node is lesser than the transmitting speed, then maybe if the receiving node has some buffer, but this buffer will overflow at some times. Okay, so in that case, to prevent the buffer overflow, we need to control the flow. Flow means that the speed of transmitting frames from the source node to receiving node. Um, okay, how the protocol works? Let's look at the stop and the wait protocol, because this is a very simple protocol that we may understand the flow control or error control concept in data link layer and in the transport layer. To understand this concept, I recommend you please open page 698 pages. There are some pushing and pulling mechanisms, and also there are some explanation about the flow control at transport layer. Okay. 707, um, there are explanations about simple protocol at 23.2.1 chapter. Okay, you can see there. And in figure 2.23.17 shows you that the simple protocol. Actually, how the protocol works, there are actually two nodes, send and receive node, and a data frame at the sent. Okay, this is data is sent now. Then what do we need? Yes, receive, if successfully receive that frame, it should acknowledge, right? X0. And then the data frame and frame 1 is now sent, and acknowledge 1 will be sent like this one. So this is very easy to understand, right? So like for example, here are two nodes, sender and receiver. Just they send out the data, and then acknowledge arrived, and then send data again. So this is very simple, and we call this a stop and wait protocol. Why stop and wait protocol? It stopped until the acknowledge arrived. After that, the new frame will be delivered. Okay, so this is stop and then deliver it. So after sending out the data, stop until acknowledgement is received. Now let's think about uh, the error control at the data link layer. If the frame is damaged, what happened? And then the damaged frame will be discarded. If not damaged, then it will be uploaded into the network layer because it's successfully shipped, right? If the frame is corrupted, that means something happened there, right? The corrupted packet is discarded. Otherwise, an acknowledgement is sent to the sender. So, what happened if some error happens? Okay, maybe there are some cases that we need to do some actions for the error control. Maybe first one is the error detection. Okay, the sender and receiver, either both or any, must understand that there is some error in the transit. Okay, and positive acknowledgement. When the receiver correct frame, then it should acknowledge it, right? And the negative act. When the receives damaged frame or some duplicated frame, it send the neck back to the sender, and the sender must transmit the correct frame. And then third case, retransmission. What does it mean? If the sender maintain a clock and set a timeout period, if an acknowledgement of a data frame previously transmitted does not arrive before the timeout, then the sender retransmit the frame, and then thinking that the frame or its acknowledgement is lost in the transit. So there are some cases error happens while sending and receiving the frames. Then maybe let's ask, how would you implement flow and error control to enable? What device maybe will you need? Maybe we need some mechanism for flow and error control. Um, at least we need some frame and check redundancy code. Also some acknowledgement and timer to count the time to get acknowledged. As the figure in page 709, figure 2320, okay, we can devise the frame with CRC, okay, acknowledgement with CRC, also timer in the sender side. So the scenario is like this. In the sending node, if the data arrive from network layer to send to the receiving node, and then the data delivered to the data link layer, and then the timer, I mean, if the frame is ready to sending out, and then it is sent out, and then timer start. Okay, then the frame travels to receiving node. If that delivered data is correct, then acknowledgement with the CRC will deliver to the sending node, and then the sending node start to deliver another frame. Our question is that what if there is a frame or packet loss? So in this case, we have to consider that maybe this is actually some node that is upper node. So data is generated from upper node and then asked to data link layer to sending out. Okay, and then the packet from network layer converted into frame, and then um, after the frame sending out, the receiving node, if receive the correct packet, then it will give the acknowledgement to the sending node. Then the correct frame now is delivered to the upper layer, such as network layer. Okay, what happened? The data frame was delivered, but while delivering to receiving node, but unfortunately the frame was lost. Okay, and then maybe the timer, it check out the timer, and then within the timer, then it resent the data frame, and then packet is successfully received, then acknowledgement will be delivered. How about the other case? Suppose frame was successfully delivered, but unfortunately the acknowledgement um, frame was lost while coming from receiving node to the sending node. And then we consider the timer is expired, right? Then it may request to resend the packet, and then acknowledgement will be delivered to the um, send. But within the if the acknowledgement could not reach to the sending node until the expired time expired, then maybe the sender will resend. Okay, so here actually we consider there are two ways that one is that the frame loss, another one is acknowledgement loss. So that's the reason for not successfully receiving the frame depend on the source node or destination node. So in any way, we need to devise some way error happens and how we can correct the error happen case. So we must say that error occurred in end data transmission. It is not. It always actually we have the possibility of error occurrence, and then for this actually we need some way of error detection and correction technique for successful communication. And then we need to think about that how the error detection process works. And later on, I will explain the Hemming's error detection and the correction code and the cyclic redundancy code too. So these are actually applied now in our internet communication. So let's back to your book in page 185. We can say that data may change or corrupted during the transmission from sending to receiving node. For reliable communication, errors must be detected and corrected. Okay, so we can say that there are single bit error while this 1 byte data is now sent to the receiver node, but unfortunately only 1 bit was corrupted or error happened. So either 0 to 1 or 1 to 0. So this is the pattern of 1 bit error case. How about 2 bit or more bit of the data parts change? We call that um, burst error. Okay, burst error. So more than 2 bit, for example, 2 bit, or actually there's some 1 bit, actually multiple bits errors happen. Okay. Main idea or behind of the error detection is that the concept of redundancy by adding extra bit to the detect errors at the destination. For example, say this receive side node, okay, or this send node. So the originally we want to send this data, but to check whether the error happens of the frame, we may add some more data there. So we call this part as data and redundancy part. Okay. Then how it works? Suppose through the medium, this data now are delivered. Okay, and then the received data. Okay, this is the received data has the same pattern. Then it may check some way whether from this one and then this redundancy will met or not. Using this, maybe we can check whether the delivered information is corrupted or not. So the error detection process works as like this. For example, in sender, it's the data word has k bit, and then some way of generator generate the code word with some data word plus some redundancy code. Okay, so then a code word now it will be delivered. Okay, so not this data word. So code was delivered through the unreliable transmission medium, and then receiving the code word, then we can pass through the checker, and then if there's some error happen there, then we may discard, otherwise extract the data word from the code word and then use it. Okay. So when the receiver knows that the original code word has been changed, then we can say that, oh, there's some error happens. So we can detect the error. Let's give some example of error checking code. For example, like a data word, now 2 bits, 0001, 1011. And then the code word with redundancy bit is there like this one. We can add up one more bit there, right? Okay. Is there any principle? Yes. The number of ones in code word should be even. Okay. For example, the data was 01, right? But for the even number of one bit one should, so we need to add one zero, otherwise 00. Okay, so there are two ones, there are two ones like this one. So this we call that even parity code. Okay, so in this case, actually, we say that k equal 2. That's the size of data words, and in addition to that, the code word size is 3 because it need data word plus redundancy bit. Okay, so this is like a 2 plus 1 is 3. Okay. So now we consider the structure of encoder and decoding error correction method. Okay, now we are considering error correction. So from the sender, we know that data word through passing through the generator, then code words are generated, and it will transmit it through unreliable transmission. And then n-bit code word will use the checker, and then create the k-bit data words. One examples of code that can be error corrected is that. So now we data were 2, but we add 3 bits data to there, no, redundancy code there. So in this case, we call that 2-bit data word, and it is composed of 5 bits code word, and the redundancy size is 3. So from 00, so we can generate 00, 01, 011, 101, like this one. So this is a kind of example that can be error corrected um, after receiving the data. There are some rules of the simple parity check code. For example, single bit error detecting. So in single bit error detecting code, we can find out exists one bit, at least, no, actually 1 bit error exists at the received code. How can it work? For example, like C54, that means that 4 is that the original data word size, and then 5 is the code word size. Code word size increases because it add 1 bit error detecting code there. So for example, like data words 000, now they say that this is a simple parity check with the odd, no, actually even parity check, even, or they could be odd parity, but let's say even parity case. So 000, so there's no ones, so just added 1. 001, the number of 1 is that 1, so we add one more 1, right? 0010, so it's when one more 1, like this. 10011, so we can add 0 there. Like this, we can put some simple parity check code through the Hamming distance code, and there are some rules. So for example, code size k bit, and 1 bit error detection for k bit data words, we need the Hamming distance at least 2. What is the minimum Hamming distance? Minimum Hamming distance is that between these two code words, the differences of each digit, we can see that that's the minimum Hamming distance. For example, in these two cases, only these 2 bits are different, right? So we say that Hamming distance equal 2. How about the other, like this one? This one also, this one got same, right? But these two different. So we say that this Hamming distance is 2. So the simple parity check code is actually adding 1 extra bit to check the error detection, and also the Hamming distance is 2. Devise some other code, like for example Hamming code 7.4, no 7.4. In 7 4 code, that's actually similarly it adds 3 more bits, because the 4 is actually data word size, right? It's 4 bit, but the 7 is a code word size. So it needs to add 3 more bits to there, and also we can use as the even or odd parity check to that. Okay. Now let's look at the example of the cyclic redundancy code. So actually, the cyclic redundancy code is usually used as a LAN or WAN. So local area network, they use the cyclic redundancy code. An example of the cyclic redundancy code is 7 4 code. So they add 3 more bits through the input data word with the 4 bit. Okay. So here actually data word size is 4 bit, but the code word size is 7 bit. So 3 bits are redundant code. They are the cyclic redundancy code, encode and decode. For example, data word, it has 4 bit data, and then the encode generator um, check the remainder, and the remainder bit will be added to compose the code word. Okay, so this is C this code. And then this code word will be delivered through unreliable transmission line. And then these 4 bits are code word, and 3 bits are also the redundancy code, and it will be checked, through the checker, and then checking the syndromes. So if the checking the syndrome, it may decide accept or discard due to the errors of the code. CRC code can be generated. For example, say data was 101, and then we have some kind of divisor that's actually code generation functions, and then we check the quotient and the remainder. For example, how we can divide the 1001 with the divisor 1011. So maybe there are 4 bit, and the first bit is 1, so it multiply 1 times 1011, so this one. Okay, and then if the same 2 bit are the same, and the value will be 0, and different one, and then 1. So it's a kind of exclusive OR calculation, right? And then 0 0 1 0 0. So the next one, we may apply 0 times this much, right? So this 0, and then the third bit this much, 1 0, and uh, 1 times the 1011, like this one. So if different 1 1, and the same 0 0, right? So the last part, bit 0 uses divisor as no, this 0 0 0. Okay, so if we add this up, then 0 1 1 0. So now we have a 3 bit remainder 1 1 0. So the code word now will be generated through the this kind of calculations, and then the code word will be used for error detection purpose. So what happened if now we receive the code word and received, okay, here received 2, and then we use the same divisor 1011 with the received 1001 code. Okay, here and we put the remainder here too. Okay, 1001 and 110. Then first we divide it through the 1011. It's 1 times it's 1011. So this and then 0 1 is different, right? So 1 and 1 is 0. So 0 1 0 1, like this one, and then 0 0 can be multiplied, right? 0 0 0. So the 0 0 1, like this one, and then finally the remainder will be 0. That means what? The data frame, that we received is correct. But what happened if instead of 1001, it changes to 1001? It's originally it should be this one, but if this bit has some error, one bit error happen. What? Let's look at then what happened. Okay, then 100 or 110 we divide through this one as a correct case, and then 1 times 1011. Okay, so 11000, and 2 times 000, right? And then 111 and nothing. Okay, 1011. So in this case, 1011 here, and then says same 0, same 0, 1, 0. So we have finally the syndrome will be 0, 1, 1. That doesn't mean what? There's some error. Okay, so we may discard this frame, or we may receive request another frame to retransmit. So from this mechanism, we can see that how we can detect the errors. Okay, so typically in frame, data and header and trailer. In here, actually, we put some check redundancy code to check whether the error happened or not.